Dear students, after studying this module, you shall be able to know what is alpha and beta cleavage, learn about allylic cleavage and benzylic rearrangement, identify McLafferty rearrangement patterns in various compounds, evaluate fragmentation pattern in a mass spectrum. Now students, let us introduce this topic by taking up alkyl halides, ethers and alcohols, and let us learn about their fragmentation pattern. Alkyl halides, ethers and alcohols show the types of similar fragmentation behavior. The first one being bond between carbon and more electronegative atom, that is oxygen or halogen in this case, it breaks heterolytically. That means the negative charge is more towards the hetero atom and the positive charge remains on the carbon atom. Second one being the alpha bond between carbon and atom of similar electronegativity, that is carbon and hydrogen, breaks homolytically. That means the electrons in a bond are distributed equally amongst the carbon and hydrogen, that is during the alpha cleavage. Those bonds are most easily broken, which that lead to resonance stabilized cations, as it is already stated in many other modules which we have dealt with mass spectrometry. During fragmentation, types of cleavages occur in ketones. Number 1 is the alpha cleavage and number 2 is the beta cleavage involving McLafferty rearrangement and ethene extrusion. Now let us study the alpha cleavage in mass spectrometry. The fission of a bond originating at an atom which is adjacent to one assumed to bear the charge is known as alpha cleavage. Now let us consider alpha cleavage in alcohols. In alcohols, alpha cleavage will occur with the fission of bond next to the functional group, that is next to the hydroxyl group. As you can see here, we have shown you what is the alpha cleavage. That means alpha bond is the one which is next to the carbon carrying the functional group, and the breaking of that bond is known as alpha cleavage, and it gives rise to a cation carrying the hydroxyl group and a radical, and this radical here in this case is R3C dot, that is trialkyl carbon radical. Now let us consider the example of one such alcohol, that is decan 4-one 7-ol with a molecular weight of 172.26. Alpha cleavage can occur from either of the bond next to the hydroxyl group. Now here students, you can see that we have shown you the alpha cleavage for alcohols in red dotted lines, which gives rise to various fragments which are of the molecular weight 43.10, that is a radical, and a cation which carries the hydroxyl group as well as the ketonic group 129.16 molecular weight, and the others are 73.07 and 99.19 fragments, that is the alpha cleavage for another portion of alcohol which can go in the other side. Now the blue lines and the red line students, they show you both the alpha bonds and both the fragmentation patterns, whether you cleave the bond in that direction, that is next to the hydroxyl group on the left hand side, or the next to the hydroxyl group on the right hand side, how cleavage takes place and what are the fragments that you can obtain from the same. Alpha cleavage in 3-methyl 3-hexanol, let us take this example of another alcohol, gives the most abundant peak for molecular ion formed by loss of largest alkyl group, that is the propyl group, then that formed by the loss of ethyl group, and least abundant is the molecular ion found by the smallest alkyl group, that is the methyl group. Now the relative intensity of molecular ion at M by Z is equal to 73, 87 and 101, decreases from 100 to 50 and then to 10% for 101 respectively. Now you can see this clearly in the figure. We have shown you the mass spectrum of 3-methyl-3-hexanol and how the intensity of various fragments formed decreases. So you can see the M by Z value of 73 has the largest intensity at 100%, followed by a 50% intensity of M by Z 87, followed by a 10% intensity for M by Z equal to 101. Now let us consider alpha cleavage in ketones after having studied the cleavage pattern in alcohols. In ketones, students, the general formula is R1COR2. The carbon atoms of the radical R1 dot are called the alpha, beta and gamma carbons. Starting with the atoms nearest to the functional group, during the alpha cleavage, fission of the ketone with expulsion of a radical R1 dot will take place. Now you can see this here, how R1 dot radical is generated. Alpha cleavage in 2-methyl-3-pentanone. Let us take up this case. It gives you fragment ions at M by Z is equal to 71, 57 and 43. Now you can see what kind of fragments are generated from this particular ketone, that is 2-methyl-3-pentanone, and what are the intensities of the fragments which are generated in this figure. Now let us come down to the discussion of alpha cleavage in aliphatic amines. Tertiary butyl amine undergoes alpha cleavage to give rise to a M by Z peak at 58 value. Now students, why will this cleave at the alpha position? Now as we have told you that tertiary carbocations are very stable, thus this cleavage is favored. Alpha cleavage in NN diethylamine gives M by Z peaks at 58, 44 and 30. This you can see clearly in figure. The alpha cleavage in NN diethylamine gives a very dominant peak at M by Z equals to 58. It is stabilized by the electron donating ability of nitrogen. Now students, you can see here how the NN diethylamine is getting cleaved and how various fragments are generated and in what intensity in this mass spectrum. Now let us consider the beta cleavage in mass spectrometry. Fission next but one to a heteroatom or functional group producing a radical and an ion is called beta cleavage in mass spectrometry. Beta cleavage in ethers. Beta cleavage in N-butyl ethyl ethers occur neither by simple bond fission with oxyranium ion formation nor by a mechanism analogous to the gamma cleavage reaction in carbonyl compounds, but instead it involves skeletal rearrangement within the butyl chain. This reaction is of some importance in N-butyl and N-pentyl but not in higher ethers, and the sharply increased abundance of the product ion at low electron energies suggests that a rearrangement is involved. N-butyl ethyl ether, that is marked as 1, shows a beta cleavage product ion with a M by Z value of 73 with a structure of C4H9O positive of similar abundance to the molecular ion, that is 4% abundance relative to the M by Z peak, which is the base peak at 59. If beta cleavage in this ether is analogous to process in ketones, then path A of scheme, which is shown in the figure, should be followed and the product ion should have the same structure as 2. Moreover, the labeled ether, third, should lose C2H4D radical. On the other hand, where oxiranium ion formation were to occur, the labeled ether would lose C2H5 radical. Compound 3 was prepared by lithium aluminium deuteride reduction of 1-butyric acid, followed by a Williamson synthesis employing ethyl bromide. The isotopic purity of the product as determined from the molecular ion region at a nominal 16 electron volt was D2 is equal to 100%. The alpha cleavage ions with the M by Z value of 87, 89 and M by Z value of 59, 61 indicate upper limits of the D1 ether of 1.8% and 2.4% respectively. Now here you can see the mechanism of beta cleavage occurring in ethers and how different parts they give you different fragments and in what kind of shape and their structure. Let us now consider, students, the allylic cleavage. This is a major type of fragmentation for alkenes leading to alkyl radical loss. Unfortunately, migration of the double bond occurs before fragmentation, so that the observation of ions of this type is of little structural value. The mass spectra of many alkenes, especially polyenes, tends to be independent of the position of the double bond, thus isomers are distinguished. As you can see here, you can see the cleavage of alkenes in this, and with this cleavage pattern in case of polyenes, because it is independent of the position of the double bond, thus isomers can be distinguished. Now, the M by Z is equal to 41 ion is the most common ion observed in the mass spectra of aliphatic compounds, together with homologues of M by Z is equal to 55, 69, 83, etc. This is shown clearly in the mass spectrum of 4-octene, and you can see how the allylic ions at M by Z is equal to 41, 55, 69 and 83 are generated and in what intensity. 1-heptene undergoes cleavage to form stable allylic carbocations. Now you can see allylic carbocations are very much stable, and you can see how they are generated in case of 1-heptene in this reaction. And considering the mass spectrum of 1-heptene, now students, in this figure you can see the mass spectrum of 1-heptene, and you can see the various cleaved fragments in this case and the intensity of the cleaved fragments accordingly. Now students, if you consider similarly the mass spectrum of 4-methyl-1-hexene, then it will tell you the cleavage will be preferably at the position where a secondary carbocation is generated and its position is marked here in the spectrum with the correct M by Z value and at that particular intensity. Now you can see here that the molecular ion peak, which is at 98, is very less in intensity. However, if you see the allylic cleavage, which gives rise to a secondary carbocation and the allylic carbocation at M by Z value of 57 and 41, these two peaks are of very high intensity. Now you realize how important it is to know the stability of carbocations when considering the fragmentation of alkenes or any such compounds which give rise to such carbocations. And as such, secondary and allylic carbocations themselves are very stable, and thus their formation is facilitated here in the fragmentation of alkenes in mass spectrometry. Now students, let us consider the formation of stable benzylic carbocation. Now here you have the orthochlorotoluene and benzyl chloride. They undergo rearrangement to form tropylium ions and show a peak at M by Z value of 91. Now you can see here in this figure the mass spectrum of orthochlorotoluene and benzyl chloride, and you can see how tropylium ion is generated for both orthochlorotoluene and benzyl chloride, and how you can see the molecular ion peak and the intensity of the tropylium ion M by Z value is there in the mass spectrum. Now, this spectrum shows you the EIMS of orthochlorotoluene and benzyl chlorides. They are both similar, and because they are dominated by tropylium ion formation. Again, if you see here, mechanism of tropylium ion is shown to you. Benzyl alcohol also undergoes rearrangement to form hydroxyl tropylium ion, which is depicted at an M by Z value of 107. Now students, the formation of hydroxyl tropylium ion is clearly shown here in the fragmentation pattern of, or the rearrangement pattern of benzyl alcohol, and you can see how it gives first of all a M by Z value of 107. Then with the loss of carbon monoxide, it gives you a M by Z value of 79 with a structure of C6H7 plus, that is the cation. And finally, with the loss of hydrogen, it gives you, because it rearranges to get the aromaticity back in the benzene ring, with this cation, it gives you M by Z value of 77. All these products can be seen in the mass spectrum. Now, let us consider a very important rearrangement. It is a McLafferty rearrangement. McLafferty rearrangement occurs in carbonyl compounds only if the gamma carbon contains hydrogen. The hydrogen from gamma carbon is transferred to an unsaturated receptor site. It is accompanied by beta splitting. In the mass spectrum, peaks from alkene and enol would occur. Now you can see here how beta splitting takes place, and the charge retention is there when the ion gains a hydrogen. And then again with the charge migration, the ion loses the hydrogen. Now McLafferty rearrangement of butanol, that is the aldehyde, produces two products, that is ethylene radical cation with the M by Z value of 28 and enol radical cation with the M by Z value of 44. This is clearly shown to you here using the McLafferty rearrangement, how the M by Z value of 28 with the ethene radical is being generated and the enol which is not detected. And again here you can see here the enol radical cation with the M by Z value of 44 which is detected, however the alkene is not detected. Now in the mass spectrum showing McLafferty rearrangement fragments in butanol, you can clearly see the M by Z value of the molecular ion peak is 72. It is a big molecular ion peak with a nice intensity, and again the enol radical at 44 has more intensity than the molecular ion, as well as the ethene radical cation also has a good intensity. So now you can appreciate the McLafferty rearrangement in case of aldehydes. Single bond cleavage of an even mass ion will typically yield odd mass products unless ion contains multiple nitrogen atoms. So this fragmentation must involve a two bond cleavage. McLafferty rearrangement in 3-methyl 2-hexanone shows a M by Z peak at 72. Now you can see here in case of McLafferty rearrangement in ketones, you can see here what are the fragments which are generated, and similarly you can see here how they are appearing in the mass spectrum of 2-methyl hexanone. And again there is a very small molecular ion peak which is at 114. Then after the McLafferty rearrangement there are two peaks at 72 and 43 of the maximum intensity, followed by a nice fragmentation pattern involving McLafferty rearrangement. And you can see how charge retention is there when ion gains a proton. Now you can see we have shown here the McLafferty rearrangement in this ketone. Now students, let us summarize this module. Students, in this module we have taught you the various rearrangements and the fragmentation patterns in various functional groups. Now alkyl halides, ethers and alcohols show the types of fragmentation pattern in mass spectrometry, as we have taught you that bond cleavage or bond between C and more electronegative atom, that is the oxygen or halogen, they break heterolytically. That means bond cleavage is heterolytic. Alpha bond between carbon and atom of similar electronegativity, that is carbon or hydrogen, they break homolytically, that is the alpha cleavage. Those bonds are most easily broken, which lead to a resonance stabilized cations. Now students, if you may remember, we have also taught you about the generation of stable secondary and tertiary carbocations as well as allylic carbocations and how they are much more favored and facilitated in mass spectrometry when the case is there. During fragmentation, alpha cleavage and beta cleavage involving McLafferty rearrangement and ethene extrusion occurs in ketones. Students, the fission of a bond originating at an atom which is adjacent to one assumed to bear the charge is known as alpha cleavage. Now students, we have taught you this in many functional groups, how alpha cleavage takes place and how the molecular ion intensity changes as well as the intensity of the fragments changes upon the alpha cleavage. In alcohols, alpha cleavage will occur with the fission of bond next to the functional group, that is next to the hydroxyl group. Now remember students, in some of the examples there were two types of alpha cleavages because both the bonds on left hand side as well as right hand side of the hydroxyl groups were available for being alpha cleaved. Now we have to decide on obtaining the mass spectrum which kind of cleavage pattern is it following, that means what is the position of the alpha cleavage in that particular hydroxyl group. Fission next but one to the heteroatom or functional group producing a radical and an ion is called beta cleavage in mass spectrometry. And students, here also I would like to reiterate that in many functional groups we have discussed in this module, we have taken up the beta cleavage in detail, taking specific examples of those functional groups. Now coming down to the most important, that is the McLafferty rearrangement that we have taught you in the previous and the current module. It occurs in carbonyl compounds only if gamma carbon contains hydrogen. The hydrogen from the gamma carbon is transferred to an unsaturated receptor site and thus it gives rise to fragments. These fragments are detected and sometimes the fragments and their intensities in the mass spectrum are more higher than the molecular ion peak. Students, if you remember, we have discussed and we have taken up specific cases like this when we were discussing the fragmentation pattern in ketones and aldehydes, etc. And we have taken specific examples of each and every single functional group, that is ethers, alcohols, aldehydes, amines, etc. in this module to let you be more aware of how the fragmentation pattern occurs in each one of these types of compounds, and thus you should not get confused when you obtain a particular mass spectrum and you are told to elucidate a compound with that.